Good morning. It's July 22nd, and this is your daily brief in science. Here's everything you need to know. Two supernova remnants may form a rare binary pair, offering a new window into how massive binaries evolved before and after their explosions. Reports in Nature Communications describe IC44, the jellyfish nebula in Gemini about 6,000 light-years away, and a nearby remnant G189.6 plus 3.3 as the possible remaining members of a single binary that both exploded in sequence. The interpretation rests on multi-wavelength data, including long-term gamma-ray observations from NASA's Fermi Space Telescope, along with X-ray, optical, and radio data. The researchers argue that the remnants trace back to a common binary system rather than independent events, with gamma-ray emissions and spectral analysis showing distinct high-energy particle populations in G189.6 plus 3.3. Ages estimated for the remnants place IC443 at roughly 8,000 to 9,000 years old, and G189.6 plus 3.3 at about 20,000 to 110,000 years, with the original stars likely having masses of 20 solar masses or more. The analysis suggests the two stars were born in the same interstellar cloud and exploded 30 to 50 light-years apart, making a chance alignment unlikely, about 1 in 1,000. If confirmed, this would be the first observed pair of supernova remnants arising from a stellar binary and would constrain models of late-stage massive binary evolution, including the timing between explosions and binary survivability after supernova events. The study emphasizes that IC443 and G189.6 plus 3.3 were in a complex environment that has historically challenged source separation. But sensitive gamma-ray imaging helped reveal the second remnant hidden by IC443's brightness. This finding relies on 16 years of Fermi-Lat data combined with X-ray and multi-wavelength observations to support a binary origin for the two remnants. The potential discovery of a binary supernova remnant system in the Jellyfish Nebula presents a rare opportunity to study how massive stars evolve in pairs and how their explosions influence their shared environment. A new study shows cooperation can emerge and endure even when selfish behavior dominates the field. Researchers combine mathematical models, evolutionary simulations, and AI agent populations to show that opponent-specific cooperation outperforms defecting strategies and remains resilient as new defectors appear. The work from Hebrew University of Jerusalem and Rutgers University challenges classic game theory by removing the need for kin selection, direct reciprocity, or social enforcement to sustain cooperative dynamics. Opponent-specific responsiveness allows individuals to treat partners differently, and this simple discrimination is enough to foster cooperation. The findings indicate that differential responses to opponents cultivate robust cooperative communities even under evolutionary pressure toward selfishness. The researchers argue this mechanism may be a fundamental stepping stone in the evolution of complex life and a broad driver in nature. Crucially, high intelligence or complex cognition is not required. Basic recognition of different partners suffices. The study also notes that cooperation can emerge in the prisoner's dilemma without kinship, reputation, or rigid social structures. These results open a path for designing collaborative AI systems, autonomous robots, and distributed computing networks. The paper is published in the Proceedings of the National Academy of Sciences and suggests that evolution does not necessarily favor defectors in every scenario. A new study suggests the Milky Way's stellar disk flipped more than 90 degrees in the distant past, likely triggered by a head-on collision with the Gaia Sausage Enceladus dwarf galaxy about 10 to 11 billion years ago. That event, the researchers say, reoriented the disk and helps explain why halo stars today rotate slowly while the disk spins rapidly. Simulations of 25 Milky Way-like galaxies show a correlation between slow halo rotation and both the ancient collision and the major disk flip, implying the galaxy's history was more turbulent than its current calm appearance. The findings are being presented at the Royal Astronomical Society's National Astronomy meeting in Birmingham. The report also notes the discovery of the extremely old star J0815 plus 4729, formed shortly after the Big Bang, highlighting parallel efforts to understand the galaxy's early history. Future mergers include the Large Magellanic Cloud, expected to have a comparatively milder impact, and the Sagittarius dwarf galaxy, which is interacting but far less massive than Gaia Sausage. The link between the Milky Way's halo rotation and its dark matter halo is highlighted, indicating that understanding the halo's origin could inform broader questions about dark matter and galaxy formation. The Gaia Sausage Enceladus event is tied to scattering billions of stars into sausage-shaped orbits and is implicated as the trigger for the disk flip, fitting into a larger story of the Milky Way's growth through mergers. Gaia Sausage is identified as the Milky Way's last major merger, a defining event that formed the central bulge and shaped the halo. The involved dwarf contained more than 10 billion solar masses across stars, gas, and dark matter. This collision was first revealed in year 2018 through Gaia data, which showed sausage-like stellar orbits linked to the Gaia Sausage dwarf galaxy as it merged with the Milky Way. Overall, the study emphasizes that the Milky Way's current structure reflects a violent past, and that disk flips and slow halo rotation should be incorporated into models of galactic evolution and interpretation of observations. A carbonaceous CO chondrite may have struck the Earth at Chicxulub, according to a new nickel isotope analysis of boundary clay. Researchers analyzed a global K-PG boundary clay layer and concluded the impactor's composition was a CO chondrite, a rare type among meteorites. The Chicxulub impact, dated to about 66 million years ago, is closely linked to the end Cretaceous mass extinction that eliminated dinosaurs and many other species. Earlier theories blamed atmospheric cooling from sulfur and soot, but the new results point to dust ejected into the atmosphere as the primary driver of the extinction climate shift. The Science Advances study re-examines the Chicxulub event and its role in the extinction, acknowledging ongoing uncertainty about the impactor's origin. Possibilities range from distant outer solar system debris to material from the outer asteroid belt near Jupiter, but researchers suggest the impactor may have come from a debris-rich region at the edge of the solar system. Key physical details include an estimated size of about 10 to 15 kilometers and an impact velocity near 64,000 kilometers per hour, creating the Yucatan crater beneath the peninsula. The composition being unusual, sulfur from the object is unlikely to be the primary extinction driver, refining the extinction mechanism rather than overturning it. Overall, the extinction theory remains intact, with a refined understanding of how the impact's composition influenced atmospheric and climatic effects. CO chondrites contain notably lower volatile elements, including sulfur, challenging the idea that sulfur was the main extinction driver, a point the study emphasizes as part of its conclusion. A climate awakening is unfolding this summer as extreme heat, wildfire smoke from Canada, and heavy rains disrupt daily life across North America. Scientists describe a compounding climate disaster in 2026, with record heat and rainfall affecting millions in the U.S. and Europe, highlighting immediate climate change impacts rather than distant projections. Experts, including leading climate researchers, warn these events reflect a shift toward more extreme conditions as long as fossil fuel pollution continues, coining the term new abnormal. Public surveys show Americans broadly feel the reach of extreme weather, though beliefs about the climate link vary by political affiliation. A National Academies report and NAS assessments attribute more extreme weather directly to human-caused climate change, reinforcing rapid advances in attribution science and policy implications. Texas saw rainfall events labeled 1,000-year events, triggering flash floods and river overflows and signaling increasing extreme precipitation due to climate shifts. Media framing emphasizes tangible, immediate threats over distant futures, urging rapid action to curb fossil fuel use. The season is defined by a new abnormal state of simultaneous heat waves, heavy rainfall, and fires driven by warming rather than isolated incidents. Extreme heat records were set in multiple regions with temperatures well above 40 degrees Celsius in interior and border areas, and near 110 degrees Fahrenheit in some locales. Persistent heat domes contributed to record highs and thousands of excess deaths in Europe, alongside heat stress in North American states such as Montana and Minnesota. Without rapid emissions reductions, this wave of heat, flooding, fires, and smoke could presage even more destructive futures. Hundreds of millions faced wildfire smoke air quality warnings, illustrating climate change already shaping daily life. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.